Yeah, so take it away, John.
Well, I got a little, the devil made me do it. I was going through the book looking at some questions in chapter 4, and I found one that I just hate. It's trick and it's hard, and I put it in. So at least you'll be warned. But of course, the questions you have to test to are a random compilation of the ones that we have here.
So we could get it, huh?
Well, yeah, you could. Or you could go to Las Vegas and miss the whole thing. Let me see here. I guess I better get it ready. Um,
Are you able to tell us what section it's in or what page?
um, well, the hard one, yeah, um, for sure. I can't seem to find it. Um, there it is. Okay. Yeah, the first one is, let me just start the slideshow and get this show on the road. Um, is just we'll we'll work up to it. The last question is the one that you know it, you know how questions are. It could be just me, it's stumped, but um, would it remember in school they had story problems, and sometimes you're like, I get it right away, and sometimes you beat your head on the wall. At least that was my experience. Okay. Oops. Did it happen? Okay.
Starting. Yes, it's on the screen.
Yay. How does a capacitor react to AC? This was just, I don't think I asked it before. Um, as frequency of the applied AC increases, the reactance decreases. As frequency of the applied AC increases, reactance increases. As amplitude of the applied AC increases, reactance increases. As amplitude of the applied AC increases, reactance decreases. And um, I hope you've got it that the reactance is a function of frequency. I mean, it affects the amplitude, but the frequency is the driving force on any kind of reactance or yeah. So, anyways, any guesses? Or does somebody really know the answer? Um,
Given your hint, I'm going to say A.
Yeah, that's what I thought. I thought the same
reactance
thing. A.
decreases. Yeah, I think that might be right. Let's see. Yay! Yeah, it
Right.
can be a function of frequency, and so like one of the stories is if you have your if you're interfering with your TV back in the antenna TV days, or even without, or even in the speaker wires, you put a small capacitor across the two lines, and the capacitor is high enough. I mean, the audio frequencies are so low, it has no effect on them, but the RF, which is, a million times higher frequency, it shorts it out and avoids the interference. Now, this one, I spent most of my career doing this stuff, so I had
Yeah.
to throw it in. And if you guys, any of you are digital people, this is like falling off a log.
Yeah. I remember this one from, learning binary system in school. Be C, I believe.
Right, right. Two to the fifth, I mean, excuse me, two to the third power
So, yeah.
is the thing. But of course, if you go through how a counter works in slow motion, it's a little more meaningful than just two to the third. Four times. Okay, now here's the one that I just this is to me was hard. I even got the page ready for you. It's page 4-3. Um,
I've
What percentage of power loss is equivalent to a loss of 1 dB? 10%, 12%, 20%, or 25%? 20.6 or 25.9. So they really nailed it down there.
Yeah, I remember this one because I missed it a couple of times on a practice test. So
Yeah,
I'll,
and the
I'll be,
example
I'll
in
be,
the book does the inverse. I went through the example, and this is what tricked me the time I thought I knew how to do it. The first time it just didn't make sense. But yeah, it's like, what percentage of power is lost? It's not which percentage of power do you have, but which percentage
yeah,
of loss. That's what tricked me.
yeah, the book does that. It does what you got left. Yeah.
Yeah, when you go through the example in the book, it says 79.4,
Uh-huh.
but that's the amount of power that gets through 1 dB a loss. So if you put 100 watts in one end of the cable, you'd get 79 watts out.
Yeah.
Loss is 20.6.
Mhm.
Anyways, I guess I gave it away, but and then I wanted to throw in a friend of mine who helped a lot with my Morse code was a principal in Royal Oak schools. He just memorized it. It's like, I don't get that stuff. He just memorized all the answers. And, the questions you will get are the exact same questions that are in the book. It is a question pool. So you can resort to just memorizing stuff too, if you're good at that. And that's the end of the quiz.
Okay, thank you, John. All right, so over the last few weeks, we've been talking about how radio signals get generated and detected in your transceiver, how current in a wire gets turned into radio waves and antennas. And tonight I'm going to talk about how radio waves travel from point to point through propagation, radio propagation. And I want to show you something here just to show you. You're probably very used to propagation on VHF, where when you're within 20, 30 miles of a repeater, you can talk to anybody else within 20, 30 miles, but that's about the limit. Well, the limit on the high frequency bands is the whole world, and I want to show you something here. I hope this shows up. This is a QSL card I got from a guy I contacted on Breaksea Island, Australia, which is off the southwest coast of Australia, and that's about as far away as you can get uh, from uh, from Royal Oak, Michigan, and still be on land. It's about 11,200 miles away, and half the farthest point from where I live, which is in the about halfway between Australia and, let's say, Madagascar, is 12,500 miles away. So at any rate, I did that with 100 watts on a wire. And so that's something that you can look forward to also. So let me see if I can get the slideshow going here. So bear with me a moment, please. Slideshow. There we go. Slideshow. Yep. Okay, now you have to bear with me while I get this actually showing on your screen. Okay, can everyone see the main slide here?
Yes.
Okay, good.
Yes.
We're going to talk, we're going to talk about propagation, and I promise this one will not run long. even though I've thrown in a couple extra things. So on VHF, you're used to point-to-point propagation. Basically, what your radio can see is what it can communicate with. And it turns out, the VHF propagates out to the radio horizon. And it turns out that the radio horizon is a little bit farther than the optical horizon, but still, your radio signals can't go, the path between the transmitter and receiver can't go below the horizon, below the Earth's horizon. For the HF bands is different. Some propagation takes place by radio signals traveling along the curve of the Earth, but mostly it takes place through the ionosphere. Now, the ionosphere is a layer of very thin atmosphere that is many miles above the Earth. And I'll get into this in the next slide. But basically, it is so thin that it's so thin that when ultraviolet radiation from the sun breaks atoms apart into ions and free electrons, it takes quite a while for the ions and electrons to recombine into whole atoms. And while these charged particles are floating around in near vacuum, they act like a conductor. Not a very good conductor, but nevertheless enough so that they influence radio signals coming up from the Earth's surface. So let's see here. So it goes from about 30 miles to 300 miles above the Earth. And let's see. Okay, so there are different layers. For what it's worth, the highest point on Earth, Mount Everest, is about 5.5 miles above sea level. The ionosphere goes from about 30 miles to 300 miles above the Earth. To give you some idea, the threshold of space, in other words, the minimum altitude where a moving spacecraft can actually complete an orbit of the Earth, is about 62 miles above the Earth. And so when you read about these space tourists that go up into space, they basically go in a capsule that gets launched and gets above that 62-mile limit, or 100 kilometers, and then comes right back down. They don't orbit the Earth. Most satellites orbit the Earth at an altitude of 200 to I want to say about 400 miles. And that's low Earth orbit. And some of them orbit beyond the top of the ionosphere, and some of them don't. And it turns out that even though the atmosphere is very thin in the ionosphere, it's enough to cause drag on satellites and to bring them down. So, at any rate, so at the bottom of the F2 layer, at about 200 miles up, there's enough drag on satellites that they'll come down to Earth after a week. But if you get beyond the top of the F2 layer there, outside the ionosphere, they can stay up for years without coming out of orbit. So the layers of the ionosphere are the D layer, which is about 30 miles up, and it exists during the day. That's when ultraviolet radiation from the sun reaches the deepest into Earth's atmosphere and the closest to the surface. And then above that is the E layer, which lasts a little bit beyond the end of daylight. Above that, during the day, are the F1 and F2 layers at 100 miles to about 300 miles. And then at night, the two layers combine into a single F layer that is somewhere between. Now, the D and E layers, the ionization goes away after the sun sets because the particles aren't being excited by ultraviolet radiation. The F layer remains ionized 24 hours a day. So let's see here. So the D layer, okay, so this just recapitulates what I said. The D layer is only present when the sun is up. The E layer goes away a little later, and the F layer, the F1 and 2 layers combine, but remain ionized and conducive to radio propagation at all times. So the E layer is similar, but it's higher and less dense, and it acts on higher frequencies. The F layer is the least dense, and the height of the F region or layer depends an awful lot on a number of things. The time of day, the season, the latitude, in other words, the distance from the equator, and solar activity. And I'm going to talk about the sun in the second half of tonight's class. So the stronger the illumination from the sun, the higher the F2 layer will be. And so it's at its maximum when the sun is directly overhead, compared to the spot where you are. Or it's the highest where directly underneath it is high noon on the Earth's surface. So this changes through the day. Now, I want you to think for a minute. This is what the whole Earth looks like divided into day and night. And this is roughly what the globe would have looked like, the whole Earth would have looked like a couple hours ago when it was still daylight in Michigan. And about this time of year, this is the path of the terminator, or the day-night boundary on Earth. So in the sunlit sides, there are separate F1 and F2 layers, and the D and E layers are the D and E layers are present. And on the nighttime side, the single F layer is still present, and the D and E layers evaporate, or they go back to no charge. So how's the ionosphere work in terms of waves? Well, the ionosphere refracts radio waves the same way that a prism refracts visible light. So I'm sure everybody's seen that picture where, whether or not they're Pink Floyd fans, of white light entering a prism on one side and coming out as a rainbow, different colors at different angles on the other side. Well, the same thing happens to radio waves passing through the ionosphere. So how well the ionosphere refracts radio waves depends on how much ionization there is and what frequency the radio wave is. And the higher the ionization, the more the refraction. And the different layers of the ionosphere act differently, and we're going to get into the detail here. The lower the frequency, the more the refraction. In other words, the more the radio wave will bend back toward Earth, passing through the ionosphere. Now that means that VHF, especially 2 meters and up, passes right through the ionosphere. 6 meters sometimes will refract, and sometimes it won't. Now, in the high frequency bands, refraction is fairly good. And so the radio waves are effectively reflected back to the Earth's surface, which is good because that way you can contact this distant stations. So VHF and UHF essentially pass right through all the layers of the ionosphere. And that's why we talk about point-to-point propagation for VHF and up. Each reflection from Earth to ionosphere and back to Earth is called a hop. The path through the air and through the ionosphere is called a skywave, and propagation via the ionosphere is called skip. So the higher, if you think about the geometry for a second, the higher the region where the reflection takes place, the longer the hop, the farther your signal will travel coming back to Earth. Or conversely, the farther away you can hear a station. So from the F2 layer during the day, single hop can go up to 2,500 miles. That's a practical maximum. From the E layer, hops can go up to about 1,200 miles because they're closer to Earth. So the other thing is radio waves that are transmitted at a relatively low angle from your antenna will travel the farthest. Because the bending angle in the ionosphere is lower, and because where the radio wave travels through the ionosphere is farther away from your station, and therefore farther away from the receiving station. So the highest angle at which you can transmit where radio waves are still refracted is called the critical angle. Above the critical angle, signals pass right through the ionosphere, and below it, they're refracted back to Earth. Critical angle depends on ionospheric conditions and frequency. Now, here are a couple illustrations on the left here. On the left here, if you look at the path from point A to point B on the globe, the solid blue line there shows that the radio signal that leaves the transmitting station at a certain angle is bent through the ionosphere and back down to where it hits the Earth, where the receiving station can hear it. But if you want to simplify that a little bit, you can imagine that is a reflection off a sort of imaginary mirror, not a very good mirror, by the way, but an imaginary mirror that is higher than the actual path that the signal takes. And so when you see a description that radio signals reflect off the ionosphere, that's sort of a simplification that that doesn't take into account the actual physics, but is good enough for a simple explanation. If you look at the right-hand picture here, if you trace out these lines, you can see that the lower the takeoff angle on the left there, the farther the path. If you look at the lowest line coming from the transmitter, you'll see that it travels through the ionosphere at the farthest distance and comes down the farthest distance away. If you look at the one marked critical angle, you'll see that it comes down to Earth at the shortest distance away. And transmission above the critical angle passes through the ionosphere. Now, it turns out there's also something called critical frequency, where if you transmit a signal straight up, come back down to Earth. I'm sorry, signals below the critical frequency will come back up and down to Earth, even though they're transmitted straight up. And as you can imagine, the distance the signal travels from your location is on the ground is not all that great. So let's see here. There we go. So critical frequency, yeah. The highest frequency where a radio wave transmitted straight up will return to Earth. And these are things that are measured every day. The critical frequency throughout the day. And there are, excuse me, also ways to measure the height of the ionosphere. Now, this part I don't believe is in the questions anymore, but it's something you should know, and that is there are a couple kinds of propagation. The first is, if you look on the left of this picture, is a ground wave where radio signals follow the curvature of the Earth. And it can be a very long distance or a very short distance. It turns out that broadcast signals, if you listen to say WJR AM in Detroit or WBBM AM, I think it is at 780 in Chicago, you can hear them during the day up to, let's say, 100, 150 miles away. If you listen at night, because AM broadcast frequencies are refracted through the ionosphere, you can hear them quite some distance away. As a matter of fact, you could be sitting in Detroit or Chicago and hear AM broadcast stations in New York, Chicago, Detroit, Cincinnati. In the wintertime, sometimes I'll listen to WSM in Nashville when I'm driving at night. I'm a secret Grand Ole Opry fan. But the other thing is, if you think about the geometry of skip, radio waves don't come down at all distances from your location. Now, what this shows here is a couple of different hops, and it's not to scale. I mean, I think the distances between these cities in the real world quite so balanced. But what this shows is, in this illustration, and just pretend that for now that these cities are affected that way, between the end of ground wave coverage and the beginning of skywave coverage, in other words, the minimum skip distance, is what's called a skip zone. Here skip means, in the skip zone, it means that radio waves will skip over that zone. And you can see on the right hand, there might be a second hop. Radio waves reflected off the Earth and then travel through the ionosphere again and come down even more distant. And so there's a range of distances for the second hop that depend on the range of different distances from the first hop. And there's also a second skip zone. Now, for what it's worth, if you're talking from the American Midwest to Europe or Japan, one of the skip distances will be to the middle of one of the oceans. And it turns out that salt water is actually a pretty good conductor, and so it's a pretty good reflector also of radio waves. But if the first skip distance comes down over land, that means that in the second skip zone, the signals will be much weaker than they are if they are over if they're reflected from salt water. So the enemy of propagation is absorption. The radio wave energy is absorbed by the atoms in the ionosphere. In the D&E regions, radio waves, especially at lower frequencies, are absorbed by the denser gases. In other words, by the higher density of atoms in the lower layers of the ionosphere. So below 10 megahertz or so, the D region will often completely absorb radio waves. So in the AM broadcast band, there's no skip at all during the day. And um, and absorption increases during the day and when solar radiation is more intense. So when we talk about the sun, I get into why that varies. So when's the best time to transmit below HF? Well, the answer is at night, when the D and E layers have disappeared. It's also the best time to listen for distant AM broadcast stations. And there are actually broadcast DXers who do just that. Listen for distant AM stations. And I'm not going to get into it, but it turns out the way stations are allocated to different AM frequencies, some of them are allocated strictly to local frequencies, where the same frequency is reused at a distance of 100 or 200 miles. And at night, they either go off the air or they operate with greatly reduced power so they don't interfere with each other. There are regional stations, and then there are, I want to say, a couple dozen clear channel stations in North America. I don't mean the company, I mean stations where only frequencies where only one station will be assigned, or if there are two of them, they will be on opposite coasts of North America. And this has a lot to do with the history of AM radio. Okay, so also, noise is another enemy of propagation. And it covers up weak signals. It's stronger, the lower in frequency you go, the stronger the noise or static. It turns out a lot of atmospheric noise, especially in the summer, comes from distant lightning. And the noise that the plasma and lightning generates travels quite some distance. So if you listen to 40 or 80 meters in the summer, there can be an awful lot of noise. It can be very strong, in fact, strong enough that it will drown out the people you want to hear. And it turns out late at night, the noise becomes much less. Also in the wintertime, the noise becomes much less because guess what? There are very few thunderstorms in the wintertime. There's also man-made noise. So that's something you have to watch out for. Noise, by the time you get to 10 meters, atmospheric noise pretty much has disappeared. So 10 meters can be very quiet, and you can hear very weak signals. In other words, they're perfectly intelligible, even though the signal strength is very low. And as you go lower in frequency, to counteract the noise, to understand somebody at the other end of the conversation, their signal strength needs to be higher at your receiver. Okay. So I want to talk about paths to other stations. If you think about a globe, if you think about a globe, the shortest distance between 2 points is not a straight line on a flat map, but rather it's a straight line. If you put a string on a globe with one thumb at your location and then pull it tight until the string goes to the other location, you'll see that there's a path that follows the curvature of the Earth. And on a flat map, on a projection that you're used to seeing, it will be a curve. So if you look at the flight path of flights to Europe or again to Asia, from northern cities in the US, you'll see that on standard maps, they actually curve far to the north, whereas the path they take is actually a straight line flying above the globe. So let's talk about this Great Circle Path. So the Great Circle Path is a line that's equivalent to a string pulled tight on a globe between two locations. The short path is the shortest distance to the other station. The long path is 180 degrees away from that and goes most of the way around the globe. So if you can't hear, say, if you can't hear a station in England very well on at a bearing of, I think it's about 50 degrees from most of us, then you could turn it around and you could turn your beam antenna around and you might hear them at 230 degrees away. And that happens sometimes. Occasionally, and it may be that the path through the ionosphere, the short path is no good and the long path is just right for signal propagation. Occasionally, you'll hear both paths. And if the length of the short path and the long path are a lot different, then considering that radio signals only travel at the speed of light, there'll be a delayed signal. So sometimes you could hear an echo on another guy's signal, and that means that that you're hearing both the long and the short path. If you're sending CW, say, where your transmitter is going on and off, and with a good transceiver, the receiver switches right back in between dits and dahs, you might hear your own signal about 1/7 of a second later. That's the time it takes for a radio signal to make multiple hops around the globe. In other words, going up to the ionosphere and back to Earth several times. This is very rare, but and you can simplify it a little bit. And remember, the diameter of the Earth is about 25,000 miles. And if you divide that by the speed of light, 186,000 miles per second, that's roughly 1/7 of a second. And it could be a little bit longer if you allow for the slightly longer if you allow for the for the length of the path going up and down from the Earth's surface into the ionosphere and back. So I want to show you something here. This relates to a question that nobody got last week because the material wasn't covered. This map I'm showing you is an azimuthal projection. And I will send you one in email after tonight that's centered on my QTH, although it's good enough for anywhere in the Detroit area or outside North America, for Chicago also. And it shows the true bearing and distance to any point on Earth from the center point of the map. So as you can see, the angles aren't what the bearings to different places aren't what you might think. Now, if you're going from Michigan or Illinois to another state, the bearings are more or less what you think, but Japan is actually northwest. You can see at about, if you follow the line, at about 330 degrees. Hawaii is at about 270 degrees, and so is California for that matter. Antarctica is, the South Pole is, of course, due south from anywhere on Earth. Australia is on the far left of this map, and you can see that it covers quite a range of angles. So southeastern Australia or Tasmania is about 250, 255 degrees, and Western Australia is about 320 degrees on the map. So it's quite a range of that's quite a range of angles for very distant points. At any rate, this is useful because the direction to if you have a directional antenna, the direction to another station might not be what you think, depending on where they are, because we tend to think of uh, the direction to another place as what we see on a traditional map, where the continents are side by side and not arranged sort of in a circle around where we are. So you can see that the shapes of the continents outside North America are fairly distorted, especially Australia. But you can sort of make out the shape of South America and Africa. They look kind of what what you're used to. And then there's another feature, and that is if the farthest distance of on the map, if the outer edge of the map is half the circumference of the Earth, in other words, about 12,500 miles, then the location of any place on that perimeter is the antipode of where you are, which is to say the farthest place away. But what happens is because of the way this projection works, that farthest away place is not a point, but instead it's a circle going around the entire perimeter. So you can actually find maps on it. If you Google antipode maps, you can see a pair of Google Maps on the screen where if you pick a location, if you pick one location, it will show the location 100 the farthest point on Earth. And it turns out in North America, all the antipodes are generally in the ocean. But if you pick, say, New Zealand, if you pick New Zealand for one location, the antipodes are in Spain and Portugal. And I think Brazil has antipodes in Russia. But that's something that you can play with. So when you talk about opposite ends of the Earth, for most of North America, it's in the middle of the Southern Ocean, a very long distance from Australia, India, and Madagascar. Well, let's do some practice questions here. I think we're doing all right for time. Yeah. So let's do some practice questions. How is a directional antenna pointed when making a long path contact with another station? A, toward the rising sun, B, along the gray line, C, 180 degrees from the short path heading, or D, toward the north? Guesses, anyone?
C.
Don't hesitate. Yeah, I hear C, Charlie. And in fact, that is the
Yes.
answer.
180.
Yep. Okay. I'll move this down here so I can see the chat also. But yeah, it's 180 degrees out. By the way, the gray line is the region of the sunrise and sunset going around the Earth. And it turns out, if you think about it, near sunrise and sunset, the ionosphere is changing, and that can do strange things and sometimes wonderful things to propagation. You might be able to make contact with stations in directions you don't expect through gray line propagation. And it's sort of a great mystery, and it's surrounded with a lot of tall tales, but it's a term to be aware of. So the answer here is C, 180 degrees from the short path. What's the characteristic of skywave signals arriving at your location by both short path and long path? A, periodic fading. B, signal strength increased by 3 dB. C, the signal might be canceled, causing severe attenuation. Or D, a slightly delayed echo. Anyone?
I think it'd be D, right? Because you would get it from
Yeah,
both places.
D delta, because it takes time for the signal to
Once
circle around the Earth.
1/7 of a second.
1/7 for the maximum distance, yeah. So that's from U to U. And somewhat less than that, but still noticeable for shorter distances, or for a smaller difference in distances between short and long path. Oh, okay. Bear with me here while I make this work again. What's the approximate maximum distance along the Earth's surface normally covered with one hop using the F2 region? 180 miles, 1,200 miles, 2,500 miles, or 12,000 miles? One hop through the ionosphere and back to Earth.
2,500
That's
C.
right. 2,500 miles through the highest layer of the ionosphere is about the practical maximum for a single hop. What's the approximate maximum distance along the Earth's surface using the E region? Same choice of answers.
Yeah, that one's 1,200.
That's
E.
right. It's only about half as far as through the F layer because the E layer is lower and the geometry is different. Which ionospheric region is closer to the surface of the Earth? I'm using region and layer interchangeably the same way your book does. Is the answer D region, E region, F1, or F2 region?
Depends if it's day or night.
Well, which one is closest to the surface of the Earth? Choose any hour out of 24.
I know.
It's D. Letter A, choice A, D region.
You're absolutely right, Kim. It's the D region. And the D region is the enemy of low frequency propagation. So what's meant by the critical frequency at a given incidence angle? That's the highest frequency, which is refracted back to Earth, the lowest frequency refracted back to Earth, the frequency at which signal to noise ratio approaches unity, frequency at which signal to noise ratio is 6 dB.
The highest frequency, which is refracted back to Earth.
That's right. Why is skip propagation via the F2 region longer than via other ionospheric regions? A, because it's the densest, B, because of the Doppler effect, C, because it's the highest, or D, because of temperature inversions? This one should be easy.
Yeah, C because it's highest.
Yep, it's C because the F2 region is highest. What does the term critical angle mean as applied to radio wave propagation? A, the long path azimuth to a distant station. B, the short path azimuth. C, the lowest takeoff angle that will return a radio wave to Earth under specific conditions. Or D, the highest takeoff angle that will return a radio wave to Earth under specific conditions. Excuse me. Anyone?
Got D?
Yes, Kim, it's D. It's the highest takeoff angle that will return a radio wave to Earth. Above the critical angle, radio waves pass through the ionosphere and into outer space. And it is frequency dependent and dependent a lot on all the other things that affect the ionosphere. Why is long distance communication on the 40, 60, 80, and 160 meter bands more difficult during the day? A, the F region absorbs signals at these frequencies during daylight hours, or B, the F region is unstable during daylight. C, the D region absorbs signals at these frequencies during daylight hours, or D, the E region is unstable during daylight hours. That should be hours.
Yeah. Well, I have to say C because I said day or night. I have to say answer C for the D. That's how you get confused.
That's
D.
right.
The
The,
D
the
region.
answer is C. The D region absorbs signals, low frequency signals or lower frequency signals during the day. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight? The F2 region, F1, E, or D?
D. The D region.
Right. Letter D, D region. Okay. I'm going to just talk for a couple minutes, then we're going to take a break right at 8 o'clock. But I'm going to talk about the sun because the sun is what powers the ionosphere, if you will, and it's also what lets us exist on Earth. The amount of UV radiation reaching the top of the atmosphere is about 120 watts per square foot. And when the sun is directly overhead and there's a clear sky, we on Earth, even in Michigan, will see about 100 watts per square foot. That's quite a lot. And you could feel in the summertime, you can certainly feel the heat of the sun, which is separate from the heat of everything around you. And because it's ultraviolet radiation, the UV is energetic enough to break apart atoms in the ionosphere. And I'm going to talk a lot about sunspot numbers and solar radiation and sunspot cycles and all of that. But I want to emphasize just before we go on break here that there is a lot that we don't know about the sun. We've been observing sunspot cycles, taking scientific measurements since 1755. And there's still an awful lot that we don't know and can't predict about the sun. So right now you're hearing a lot about auroras and you're hearing about coronal mass ejections. And if you read the tabloid newspapers or some of the more excitable people on social media, right now people are saying, well, satellite communications can be disrupted and uh, and uh, electric power knocked out. Whereas when there were no sunspots on the sun at the bottom of the last cycle, people were saying, "Well, gee, we're about to have another ice age and all kinds of weird stuff like that." And I think I've just lost my video. You'll have to pardon me here while I get it back. Okay, let's do that. Yeah, here I am again. Okay. So I'm going to talk about, after the break, I'm going to talk about what we know and what we don't know. And there's some interesting things going on. What you need to know right now is that we're probably at or near the peak of sunspot cycle number 25. And so the way the high frequency bands act right now is actually pretty good. And in about 5 years, it won't be so good. So on that note, why don't we take about a 10-minute break and then come back at about 10 past 8, if that's all right with everybody.
Yeah.
So I want to spend just a minute here, if I can find it. Yeah, I want to spend just a minute here on a topic that's not on the test, but you're going to run into, and that is, since we're talking about maps, I want to share my screen for a minute here. Whoop, I want to share my display here for a minute. Let's see. Hello. What are people seeing on the screen here?
EN82.
No, that's not what I wanted.
Uh-oh.
All right, let's see if I can get back to this here.
It's the grid square map around
Oh, you're
Birmingham.
seeing you're seeing the grid square map.
Yeah.
Okay. Yeah, okay, because I'm not seeing that quite. I want to talk just a minute about grid squares because you will run into these. Around 1980, some hams in England developed a system for quickly locating somebody on the face of the Earth, and it was named the Maidenhead Grid Square System from the place in England where they held a meeting to decide this. And I'm showing a little map here. I'm going to send out an email after this class tonight with some useful information on it. But what you're going to see is you're going to see people talk about their locations. Well, in fact, all of us here in Southeast Michigan are located in grid square EN82, which is 1 degree of latitude by 2 degrees of longitude wide. So the EN divides the first two letters are a place on an 18 by 18 grid that covers the Earth, and then the two numbers after that are a 10 by 10 grid inside the larger one. So that's where we get 1 by 2 degrees, or about 60 miles north to south and roughly 100 miles east to west at our latitude, and roughly the same for Chicago. And then you can get even smaller. You can divide it up smaller. And so the two lowercase letters after that are locations just a few miles on the side. If you're not familiar with the Detroit area, those I want to say that those smaller grid squares in the map are about 5 miles north to south by 8 or 10 miles east to west. But what you will see is people will give their locations as a grid square, either 4 characters or 6. And you can actually go even farther, dividing it down to square inches, but that's only if you're real fanatic about it. But I wanted to mention this because it's something that will crop up since we're talking about maps and location on the Earth. People use their grid squares and other people's grid squares to find their locations and to get beam headings. And some of the information I'll send is websites that let you do that. Okay, so I'm going to kill that and go back to the slideshow now. So we're going to talk about the sun and its effect on propagation. All right, where is it? Slideshow. All right, so is everybody seeing the slide there that says section 8.2?
Yes,
Are
we
you
do.
seeing? Okay. So on the right here is a chart of sunspot cycles since the 1950s. It turns out in the 20th century, the most active sunspot cycle was it had a peak in 1958, and you can see the sunspot number here was very high. The weakest sunspot cycle was the previous one to where we are now, cycle 24, and you can see that the peak sunspot number was only half of what it was in the in the cycle before 1960. So sunspot cycles vary quite a lot, and you can see within the sunspot cycle, the sunspot number is very noisy. In other words, the numbers go up and down quite a bit. Now, let's talk about that. Okay, so the sunspot cycle or solar cycle lasts about 11 years, and it's usually measured from the trough of the cycle. In other words, the minimum number of where the minimum number of sunspots occur. And the sun can have no sunspots for a year or two at the minimum. And so there are more technical ways that NASA and NOAA determine the sunspot cycle, but we won't get into that. Suffice it to say that they are roughly 11 years, although they're not. Some are stronger or weaker than others, and some are longer or shorter than others. Much of the variation in the radiation that reaches Earth, sunspot activity, but what we're really talking about is the sun is this huge fusion reactor that converts hydrogen to helium, and it radiates at a whole variety of frequencies or wavelengths ranging from infrared, far infrared to far ultraviolet and even X-rays. And it's those very short wavelengths, ultraviolet and X-rays, that excite atoms in the ionosphere. So the correlation isn't 1-to-1, but when you see more sunspots, the amount of ultraviolet radiation, or the amount of electromagnetic radiation reaching the Earth from the sun, is higher. And the higher the UV, the better the ionization, the better the propagation above 10 megahertz. Now, I also want to say, if you look at pictures of the sun, it's where you can see some detail of the surface. It's very chaotic. We tend to see this very bright disk when we look at it, and unless you use special filters, you really can't see much detail. But the sun is actually very chaotic, and sunspots are part of the chaos. They're actually cooler spots on the surface of the sun. So, at any rate, let's go a little bit forward here. So, when the book was published, the sunspot cycle was still increasing, and some people think that right now we are at or near the peak. So this year and next year are probably going to be where the peak of the cycle is, and where the best propagation will be for the next 6 or 8 years. In other words, till we go toward the peak of the next sunspot cycle. So at the peak of the cycle, there may be sufficient radiation to keep the F layer ionized enough to make long distance contacts on 10 meters, 28 megahertz after sunset. Usually 10 meters fades out right after sunset, but it's possible that 10 meters can stay open well past. So, we think of 10 meters, 12, 15 meters as daylight bands, but right now it could stretch longer. The high ionization makes 80 and 160 meters propagation on those bands worse, and that's also 24 hours a day. So 80 and 160 meter propagation, the lowest HF bands work better at the bottom of the sunspot cycle, when there's less, when the solar radiation is less. It turns out, and when solar activity is low, the lower HF bands are better. The higher HF bands, 15 meters and up, are often closed. In other words, there's not any good propagation anywhere. The 20 meter band, on the other hand, is reliable. You can get long distance propagation often 24 hours a day, especially now when the sunspot number and the solar flux are high. So science has been trying to predict the solar cycle for a couple of centuries, and we're still, frankly, even with satellite observations and sophisticated models and very smart people looking at it, we're still not very good at it. I want to show you. I want to show you a couple of things. This is a very recent. This is a very recent picture from the. This is a very recent picture from the Space Weather Prediction Center, which is run by NOAA and NASA jointly. What you're seeing here, on top is the sunspot number, and the black line are more or less daily observations. The purple line there, the thick purple line, is a smooth number, the average over I think a month's time. So it lags the daily number by quite some amount. Back during the last solar cycle, when the activity didn't get very high. I also want to point out that that bottom graph is solar flux, and that is measured at 10.7 centimeter wavelength, or I think that's 2400 megahertz, because that is that the solar flux at 10.7 centimeter wavelength correlates very well with ultraviolet radiation getting to the Earth. And you can see that there is a reasonable correlation between the solar flux, which is a stand-in for the total solar radiation, and the sunspot number. So when we say sunspot cycle and solar cycle, we mean more or less the same thing, even though sunspots themselves don't cause much of an increase or decrease in the electromagnetic radiation from the sun. That pink band was the prediction made near the end of the last solar cycle. Because the last cycle was relatively weak, they thought that the official prediction center thought that the pardon me, that this solar cycle would also be relatively weak. Excuse me. But what's happened is the this solar cycle has outperformed people's expectations by quite a bit. And so, as a matter of fact, daily sunspot numbers, I've seen 230, 240 just in the last week, and that may not be the peak of the cycle yet. And so the predictions have been revised a couple of times. It turns out that around 2020, there was a group at the University of Colorado that said, no, this isn't going to be a lousy cycle. It's going to be one of the stronger ones. And everybody scoffed at them. It turns out they may be more right than wrong. And so the thin purple line and the purple bands you see toward the right of these, in the right half of these graphs, are the revised predictions from the government's Space Weather Prediction Center. And it shows that where we are right now in 2025 is probably near the peak, or the peak might occur next summer in 2026. But it's going to gradually decline, and the solar cycle will be at a minimum in 2032, which is about 7 years from now. The thing is, we don't know. This is just everybody's best guess. But it shows the cyclical nature of the sunspot cycle a little bit more smoothly, and it shows the correlation between what we can observe with our naked eye and what we can observe with radio receivers that listen at the solar flux wavelength that everybody agrees on, and what the sun is actually doing in terms of sending radiation toward the Earth. So that's a couple things to keep in mind then, that solar cycles are cyclical, that they in the long term and they vary in the short term. This is a different view of this. The that red line there was the University of Colorado prediction, and the purple line and the line were the original. The light blue line was the original prediction made before 2020. The uh, the purple line that's a little bit to the left of it is the prediction that was made is the revised prediction that shifts the original one sooner by 6 months. And now, and the green line is what typical solar cycles have done. What the average solar cycle has done since we started observing them in 1750. So you can see that the solar cycle is going on now. If you look at the black line, which is the smooth sunspot number, you can see that it's following that green average line pretty well and is really not too far off from the red line that was the outlying prediction 5 years ago. Now you also notice in the upper left that this graph was put together by a science agency in Australia, where they may not be as biased toward official predictions as we are here in the States. So at any rate, what I'm trying to say here is that predictions of the solar cycle and predictions of propagation are indications that are helpful, but you can't take them as gospel. They're worse than predictions, worse than weather predictions.
Les, I worked with some Austrians, and they would have been upset calling them Australians.
Oh, is that Austria? I'm sorry, Austria.
It's very small letters, I'll admit.
I'm sorry. But it wasn't Aussies. Okay.
Yeah, I
Well,
always love to tease them.
East Europeans might take a different view of our official predictions than we do also.
Yeah.
So, all right, back to the official slides. There's a chart in your book that talks about different bands, different HF bands, and what you can do during daytime and nighttime. And what you have to remember here is that how effective they are at long distance communication depends on where you are in the seasons, because in the northern hemisphere winter, obviously there's going to be less sunlight, and so the ionosphere in the northern hemisphere is going to get less excited. And at the peak of the sunspot cycle, the ionosphere will be more strongly charged, and in the trough, in the lowest point, it'll be less charged. So depending on the strength of the solar cycle and the season, during summer and at the peak of the sunspot cycle, the higher bands will work better and and the lower bands will be worse, and vice versa at the low point in the sunspot cycle or the winter. So right now we're in autumn, and the southern hemisphere is having their spring, so it's sort of right now around the average. But you can see that the lowest three bands in the high frequency spectrum are not very good during the daytime, and you won't hear much you'll hear hardly any activity. And at night, they can open up quite a bit. As a matter of fact, I've made contact with Europe at night, although near their sunrise is when you can hear them the best. 40 and 30 meters are regional bands during the day, and can be medium distance to worldwide at night, and they also work at short range. 20 and 17 meters are often open 24 hours a day to various places, and are open well before sunrise and beyond sunset, where you are locally. 12, 15, and 10 meters are primarily long distance during the day, and at night are usually closed, which is to say, if you're very local to somebody, if you're within 10 or 20 miles, you can use it for local chat. Although I will say that more than once, I've tuned across 10 meters at night, and I hear a couple of guys who are just chatting back and forth with each other, as if 10 meters were VHF simplex, but I can hear them here, although they might be located in Massachusetts or Georgia. So this is a good table to memorize because there will be questions about it. And when you get some experience, this will sort of be ingrained. It will come naturally to you. Okay, where are we here? Whoop, sorry. Another thing to know is that sunspots move across the sun's surface roughly every 28 days. It's not exact, and how quickly they move across the sun's surface depends on actually the latitude they are at the sun. It turns out the closer to the equator, the more quickly they go around the sun. But propagation is similar every 28 days or so. So if you made contact somewhere today, then 4 weeks from today, chances are good that you'll have the same conditions to contact the same place. And that's actually a useful thing to know. There we go. So I was talking earlier about the correlation between the smooth sunspot number and the 10.7 centimeter solar flux and the total radiation from the sun that impinges on the Earth. And you can see that the solar flux index is reasonably well correlated to the long-term smooth sunspot number. It's not exact, but is a good indication. So when you see high sunspot numbers, that means that the solar flux is also likely to be fairly high. Now for solar flux, you can see there are a couple of indexes that show up. There's the K index, that is the short-term stability of the Earth's geomagnetic field, and that is to say, is it steady or is it disturbed? And the A index is a longer-term index. And for both of these, low values are good, high values are not. And so we're going to talk about some of the reasons why very shortly. So is monitored by solar observatories around the world that cooperate, and it turns out that in the short term you can get reasonable predictions based on current conditions. Again, they're not exact, but they are good enough to be useful. If you remember weather predictions from 20 or 30 years ago, you know that they've gotten a lot better. So if the weatherman on TV says that 3 days from now it's going to be sunny and 75 degrees, then the chances are good it will be sunny and 75 degrees. But 30 years from now, you would say, well, we can hope it's going to be like that. And that's about the state of propagation predictions today for radio. So let's go through some practice questions here. How does a higher sunspot number affect HF propagation? The higher sunspot numbers generally indicate greater likelihood of good propagation at higher frequencies. The lower sunspot numbers generally indicate greater probability of sporadic E propagation. Does a zero sunspot number indicate that radio propagation is not possible on any band? Or D, does a zero spot number indicate undisturbed conditions? Anyone?
You gave away the answer. It's A.
Oh, I did already. Yeah, it's A. Higher sunspot numbers, better propagation at high frequencies. Sorry about that. Let's see if I can
No,
do this with arrows so I'm not scrolling right over these things. Which of the following are least reliable for long distance communications during periods of low solar activity? 80 and 160 meters, 60 and 40, 30 and 20, or 15, 12, and 10 meters? Long distance, low solar activity.
uh,
Anyone?
D.
That's right. D, the highest frequency bands or shortest wavelength bands. What is the solar flux index? A measure of the highest frequency that's useful for ionospheric propagation. Uh, B, a count of sunspots adjusted for solar emissions. C, another name for the American sunspot number, or a measure of solar radiation at the 10.7 centimeter wavelength.
Uh, let's see, D.
Yep, the answer is D. 10.7 centimeters was chosen because uh, even though that's in microwave frequencies, it's not absorbed by moisture in the atmosphere as well as other frequencies. And so it's a good analog for it's a good indication of total electromagnetic radiation reaching the Earth. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours? A, at the summer solstice. B, only at the maximum point of the solar cycle. C, only at the minimum point of the solar cycle. Or D, at any point in the solar cycle.
Yeah, I
Guesses,
think it's
anyone?
D. It's D, I believe.
Yep, D is the long distance band that's reliable almost all the time, regardless of day or night, or where we are in the solar cycle. What causes HF propagation conditions to vary periodically in a 26 to 28 day cycle? A, oscillations in the upper atmosphere. B, cyclic variations in Earth's radiation belts. C, rotations of the sun's surface layers around its axis. Or D, the position of the moon in its orbit. Anyone care to speak up? Anyone besides Keith?
Yeah, I was going to say, I hate to be that guy.
Well, the sun. It's the sun. Rotation of the sun's surface layers around its
That's right,
axis.
Charlie. Uh-huh.
It's not the moon. It's not the earth.
Right. What does the K index measure? The relative position of sunspots on the surface of the sun, short-term stability of the Earth's geomagnetic field, short-term stability of the sun's magnetic field, or the solar radio flux at the National Bureau of Standards in Boulder, Colorado. Anyone?
I mean, I'll jump in. I think it's B.
I'm sorry?
Is it B as in boy?
It is B as in boy, short-term stability. That's right. Or although a lower number is better.
Hmm.
And why is my video off again? I'm going to try and have everything moved over to the new computer next week so that you can watch me in my full glory all the time. Oh, A index. What does that measure? Relative position of sunspots, about a polarization of the sun's electric field, the long-term stability of Earth's geomagnetic field, or solar radio flux at Boulder, Colorado. A index. Yeah, it's different from the K index, which is short term.
So it's C.
Yeah, C, the long term stability. And The A index numbers can go much higher, but still, the lower the number, the more stable the Earth's magnetic field and the more stable propagation will be. Which of the following is typical of lower HF frequencies during the summer? A, poor propagation any time of day. B, worldwide propagation during daylight hours. C, heavy distortion of signals due to photon absorption. Or D, high levels of atmospheric noise or static. 160, 80, 40 meters.
Jump in again. It's D.
The answer is actually D.
Yeah, right.
Now, these lower frequencies have poorer propagation during daylight hours, but you still around the clock will hear atmospheric noise from static discharges, from lightning discharges. Okay, so let's talk about assessing propagation. There are measures of propagation from point to point. In other words, if you want to talk to say somebody in let's say Munich, Germany, you want to talk to somebody about Oktoberfest. Over that point to point circuit, there is a measure called the maximum usable frequency, which is the highest frequency at which propagation exists between 2 points. There's the lowest usable frequency, which is the lowest frequency that's usable for propagation between 2 points. And below that frequency, okay, above the maximum usable frequency, radio waves travel through the ionosphere and are not refracted back to Earth. Below the lowest usable frequency, radio waves are absorbed by the ionosphere. So it's in between those two frequencies where propagation is possible. They depend on the specific path. They depend on atmospheric condition, on ionospheric conditions. So they vary with the time of day, the season, the amount of solar radiation, the stability of the ionosphere. Operating near the maximum usable frequency often gives the best results because absorption is the lowest just below the MUF. And one way to check for actual band conditions is to listen for propagation beacons, which are on several bands. And there are many stations. There are many stations in the sort of beacon allocation that is agreed to by gentleman's agreement that will tell you where 10 meters is open, and you can listen for yourself. And to make contact with a distant station, you have to use a frequency between the LUF and the MUF. And I'm going to give you a couple illustrations in a moment here. It's possible for the MUF to be lower than the LUF. That may sound a little contradictory, but it happens, in which case propagation to a distant place is not possible. Isn't possible at all. So I'm going to show you a couple of charts of the type that used to run in QST magazine. These are hard to find nowadays because you can get online propagation predictions that are up to the minute. And if you look on anyway, these are monthly propagation charts that are based on the predicted sunspot numbers a couple months ahead. And this was back before the internet days when everything was instantly accessible. But it's a good indication of how how propagation changes over the day and for different paths. Now, this left-hand thing is from mid-USA, so let's call that Kansas. The East Coast, let's call that, I don't know, New York, New Jersey. The three lines here are, the blue line at the bottom is the lowest usable frequency. The green line is is where you have a 50% chance of it being the maximum usable frequency, and the red line above that is the maximum usable frequency that covers 90% of the time, which is to say that it is actually less likely, but 90% of predictions, this is sort of the outlier, and you can expect to get through on frequencies between these two lines only about only 10 to 40% of the time. And above this red line, you can expect to get through only 10% of the time. So if you look here, the scale on the bottom is GMT, Zulu time, which is uh, uh, which is 4 or 5 hours ahead of Eastern Standard Time, depending on whether it's daylight saving time. And the frequency and the scale on the left are frequencies in megahertz, but the lines going across indicate where the ham bands are. So if you notice, the highest horizontal line is at 28 megahertz. Below that at 24, 21, 17, 14. So if you look at those horizontal lines, those are the ham bands. And if you look at where the ham bands are between Kansas and New York, let's say, when it is midnight Zulu time, which is about 8 p.m., which is 7 or 8 p.m. depending. In other words, just after sunset, you'll see that 40 and 80 meters are going to be open on this path. When it's the middle of the day, 16 hours Zulu is 11 o'clock or noon Eastern, or an hour earlier Central. You can see that first of all, 80 meters is going to be closed because it's below the blue line, but there are three bands that are probably going to be reliable between the two lines here, and one band that might work 20 meters might work for a couple of hours in midday. Now, I've forgotten what month and where in the sunspot cycle I found these, but these are typical of what happens. Now, the path here is going to be less than 1,000 miles. If you look at the middle of the USA to Japan, which is several thousand miles, you see that it's much different. Look here, the blue line, the lowest usable frequency, is above the green and red lines, which are the maximum usable frequency for most of the day. And you'll see that on this path that the LUF dips down below the MUF, and ignore the red line for a minute. Between the green and blue lines here, for maybe an hour or less, and 40 and 30 meters might be open then when it is late morning in the US and the middle of the night in Japan. But then as you get towards sunset, you'll see that the path opens, and you can get through on, you might be able to get through on 40 meters, which is actually below the blue line, but certainly on 30 and 20 meters. And this kind of thing is typical for longer paths. And it all depends on what the ionosphere is doing in the places where radio waves between your station and the distant station are likely to pass through the ionosphere, which could be in one region, it could be in a couple different geographic regions, depending on the number of hops that it takes to get to that distant station. Nowadays, there are propagation services that will do things instantly based on the up to the minute sunspot number, and will give you a worldwide map on different bands for the current conditions and the predicted conditions in a few hours, or we'll give you a sort of table of how well you can expect to get through to a distant location at different hours on different bands. So it will be a tabular version of this graph, but again, up to the minute. And that's going to be in the email if you want to look at that stuff later. But the point I have here is that the bands where you get propagation between 2 points vary with time of day, and they vary on the path with the path between two locations on Earth, even on the same day at the same hour. So, okay, so this is this table at the top here is what you'll often see on websites, or you see one that's a little bit smaller. People stick it on their ham radio websites. QRZ.com has a small one like this that will show you. If you look on the upper left there, I took this earlier today, at about a little before the class started. You'll see the solar flux index at the upper left there, right below the date and time. Sunspot number SN, the A index and the K index, which actually mean things are pretty calm, and a couple other measurements, I'm not sure exactly what. And then on the right-hand side, you'll see everything simplified to band conditions day and night. And you'll see that today the predictions are in North America, at least. For North America, propagation is going to be good on all the HF bands except 80 and 40 meters at night. I'm sorry, 80 and 40 meters during the day will be poor, and 12 and 10 meters at night will be poor. Now you'll notice that 160 meters is not on this chart. There's a reason for that, and that is that propagation predictions are not very good, are really poor for 160 meters. It's very hit or miss. And so most prediction sites will not predict conditions for 160 meters. This chart on the bottom shows the K index for at different points for the last week, and you can see that it varies somewhat. So the K index, you can see on the 10th and 11th of October, it was very high. The ionosphere was very disturbed, but you can see that right now, I'm sorry, you can see that on the 14th of October, 13th and 14th, it was pretty low. And depending on the time of day, it was real low or very moderate. So these are the kinds of things that you'll see online that are sort of summaries of what propagation is doing. So you can get a broad overview, you can get detailed predictions, and you can get long-term predictions, depending on where you look. Well, let's talk about disturbances. You've heard a lot about auroras this year, and we'll talk about what happens when the sun is disturbed and how that disturbs the ionosphere. Because the sun is active and a little bit chaotic, sometimes there will be flares on the surface of the sun where hot gases will rise up from the surface, and when they do, they increase radiation. coming from the sun. This is a short-term thing. And it takes about 8 minutes at the speed of light for this increased radiation to reach the Earth. And if it's high enough, it increases the ionization of the ionospheric layers enough that it can, and especially ultraviolet and X-rays, when it reaches Earth, the radiation can cause increased ionization and absorption. If it's strong enough, it will reach down to the D layer, which will increase absorption at all frequencies. And the solar flare can cause brief radio blackouts from medium to from minutes to a few hours. There are also coronal holes in the outer layer of the sun, and plasma, which is charged particles, will escape, and things called coronal mass ejections, which you've probably heard about in the news this year, where the sun throws off large amounts of material from its outer layer or corona. Now, these can take hours to a couple of days to reach the Earth, and when they do, they disturb, because they're charged particles, they disturb the Earth's magnetic field. And okay, so I'm sorry, solar flares, which are just ultraviolet and X-rays, can cause brief disturbances. They can cause radio blackouts, and the lower bands are more strongly affected. Now, this never affects VHF. The higher HF bands sometimes, and the lower HF bands more often. And they only affect the sunlit side of the Earth because it's just solar radiation. It's not charged particles. But when you get to the solar wind replenishes charged particles because there's a steady flow of charged particles from the sun. It affects the magnetosphere around the Earth and the ionosphere. The magnetosphere is the Earth's magnetic field in 3 dimensions. But anyway, the solar wind will cause the Earth's magnetic field, first of all, to get stronger, and second, to sort of tail off behind the Earth on the night side of the Earth, and that's normal. But charged particles from coronal holes, and especially coronal mass ejections, if they are aimed at Earth, or if they graze the Earth's magnetic field, they can increase ionization in the E region and create a so-called geomagnetic storm, which affects the higher HF bands. And also, if there are enough energetic particles reaching the Earth, they can cause auroras, which are basically charged particles from the sun causing plasma trails through the lower layers of the ionosphere. So geomagnetic storms affect higher HF bands, and they can disrupt communications for hours. And auroras are deadly for HF communication. They will absolutely kill all the HF bands. Once I was operating at an event in Rogers City, which is up not too far from the Straits of Mackinac. We had 3 stations on the air, and all of a sudden we weren't making contacts. This was during Museum Ships Weekend, where museum ships, like light ships that have been docked, for instance, or old aircraft carriers that are permanently docked, and museums about ships get on the air. So we were doing that in Rogers City, and all of a sudden the HF bands went dead, and we went out and looked, and sure enough, on the north shore of Lake Huron, across on the Ontario side, there was a green aurora just above the horizon. So if there are auroras out, or if the newspaper says the likelihood of aurora is high, which this year and next it's going to happen again, then HF propagation will be no good. And also, because auroras are common in the high latitudes, north and south, pass over the North Pole, for instance, between Michigan and India, or Michigan and much of Indonesia, usually don't work very well. So there's a whole wide swath of Russia and in India that are very hard to reach from the Midwest of the US because of this, because propagation due to aurora and due to geomagnetic influences over the poles is very iffy compared to propagation in other directions. So, yeah, there we go. So, however, in the VHF bands, sometimes you can get propagation signals bouncing off auroras because they're charged particles. So if they're energetic enough, they act the same way. The particles that comprise the aurora act the same way as the ionosphere does for lower frequencies. And I played during the first class session, I played an excerpt for you, and they are buzzy because what you're they're reflecting off of these particles traveling through space, and so it's very irregular. It's not a sort of steady sheet of charge, but rather random charged particles that are passing by. So, okay, so here we go. So let's do some practice questions. We're getting sort of near the end here, which is good. I will try and wrap up in the next 10 to 15 minutes, and we can call this chapter done if everybody's okay with sticking around for a little bit longer. What effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation? A, it enhances propagation at all frequencies. B, it disrupts lower frequencies, propagation at lower frequencies more than at higher frequencies. C, it disrupts communications via satellite more than direct communications. Or D, none, because only areas on the nice side of the Earth are affected. Now, I'll give you a hint. Sudden ionospheric disturbance is only electromagnetic radiation. It's only ultraviolet and X-rays. So anybody care to guess what the answer is?
It would be at higher frequencies.
Yep, that's right. The answer. So it disrupts signals on lower frequencies, because if you recall what I just said, the increased solar flux, the increased UV and X-rays, well, the increased UV mostly penetrates through the atmosphere enough that it increases the ionization of the D layer, which absorbs radio signals better. Approximately how long does it take the increased ultraviolet and X-rays from solar flares to affect radio propagation on Earth? 28 days, 1 to 2 hours, 8 minutes, or 20 to 40 hours?
C, 8 minutes. I know that one.
Yep. Speed of light from the sun to the Earth, 8 minutes. What's a geomagnetic storm? A, a sudden drop in the solar flux index. B, a thunderstorm that affects radio propagation. C, ripples in the geomagnetic force. Or D, a temporary disturbance in Earth's geomagnetic field. I'll give you a hint. It's not Star Wars.
D?
Yeah, it's D, a temporary disturbance caused by charged particles interacting with Earth's magnetic field. How can a geomagnetic storm affect HF propagation? A, improve high latitude HF propagation. B, degrade ground wave propagation. C, improve ground wave propagation. Or D, degrade high latitude HF propagation.
I believe it's D again, right?
It is D again, yes, yes. And high latitude, if this geomagnetic storm is strong enough, high latitude includes us here in the upper Midwest. How can high geomagnetic activity benefit radio communications? A, it creates auroras that can reflect VHF signals. B, it increases signal strength for HF signals passing through the polar regions. C, improves HF long path propagation. Or D, reduces long delayed echoes. Anyone?
A.
Yep, it's A. Creates auroras that can reflect VHF signals, although it's not very reliable. How long does it take a coronal mass ejection to a radio propagation? A, 28 days. B, 14 days. C, 4 to 8 minutes. D, 15 hours to several days.
Several days. D.
Yep, the answer is D. It's the amount of time it takes for charged particles to reach the Earth, and they're traveling much slower than the speed of light. So half a day or 3/4 of a day to several days. Usually within a couple of days is when you'll see the effects. If any of you follows the Hazel Park Club page on Facebook, there's a guy who posts information every day about solar activity, and sometimes he'll say coronal mass ejection that is likely to miss the Earth or was likely to hit the Earth, and he'll say about how long people think, how long science thinks it will take to reach the Earth. How is long distance radio communication affected by the charged particles that reach Earth from solar coronal holes? A, HF communication is improved. B, HF communication is disturbed. C, VHF and UHF ducting is improved. D, VHF and UHF ducting is disturbed. Anyone?
It's a total guess, but I would guess B.
Yeah, it's Bravo. Charged particles from coronal holes are lower intensity versions of what happens when there's a coronal mass ejected. So in terms of coronal holes, particles are sort of leaking out from the sun's surface and from coronal mass ejections. A whole bunch of them are thrown off the sun. What factors affect the MUF? A, the path distance and location between 2 points. B, the time of day and season. C, solar radiation and ionospheric disturbances. Or D, all of the above. This should be easy.
All of the above?
Yep, all of the above.
Okay.
Which frequency will have the least attenuation for long distance skip propagation? A, just below the MUF. B, just above the LUF. C, just below the critical frequency. Or D, just above the critical frequency.
A.
That's right. The answer is A, just below the maximum usable frequency. So if you see from propagation predictions that there's an opening to some distant point on several bands, you want to try the highest band first. Which of the following is a way to determine current propagation on a desired band from your station? A, use a network of automated receiving stations on the internet to see where your transmissions are being received. B, check the A index. C, send a series of dots and listen for echoes. Or D, all of these choices are correct. I'm sorry, this is in your book, but I didn't say anything about it tonight.
It's A.
Yeah, the answer is A. This network of automated receiving stations is the reverse beacon network, or RBN. And you can see RBN spots. You can see RBN spots on several websites, and if you're a little bit savvy, they don't even have to be from you. You can go by call area, or sometimes there are other indications of where signals are being transmitted from. How does the ionosphere? Oh, also you can listen for beacon stations. How does the ionosphere affect radio waves with frequencies below the MUF and above the LUF? A, they're refracted back to Earth. B, they pass through the ionosphere. C, they are amplified by interaction with the ionosphere. Or D, they are refracted and trapped in the ionosphere to circle Earth.
A.
That's right, A. Between the MUF and the LUF, ionospheric propagation is possible. In other words, signals are bent back to Earth. What usually happens to radio waves with frequencies below the LUF? A, they're refracted back to Earth. B, they pass through the ionosphere. C, they are attenuated before reaching the destination. Or D, they're refracted and trapped in the ionosphere and circle the Earth. This wording is a little bit tricky.
This one wrong. When I did the practice test, I think is it C, or is that one of the wrong answers I kept giving?
Yeah, the answer is C. They're attenuated because the signals are absorbed by particles in the ionosphere.
I kept wanting to say B, but that's wrong. Because we're talking about the lowest usable frequency, right?
Yeah. What does LUF stand for? Lowest usable frequency? Lowest usable frequency lowest usable frequency between two specific points, lowest usable frequency to any point outside a 100-mile radius, lowest usable frequency during a 24-hour period, lowest usable frequency during the past 60 minutes.
You just gave the answer. It's A.
Yeah.
Yeah, it's A. It's A. Lowest usable frequency depends on the path and ionospheric conditions, and it's different for different distances and directions. What does MUF stand for? Minimum usable frequency for communication between 2 points, maximum usable frequency for communication between 2 points. Minimum usable frequency during the 24-hour period, maximum usable frequency during the 24-hour period.
Got to be between 2 points. B.
That's right. B, maximum usable frequency between 2 points. What happens to HF propagation when the LUF exceeds the MUF, when the LUF is higher than the MUF? A, propagation via ordinary skywave communications is not possible over that path. B, HF communication over the path are enhanced. C, double hop propagation is more common along the path. Or D, propagation over the path on all HF frequencies is enhanced.
A.
Yep, when the lowest is higher than the maximum, you can't get there from here. Okay, we're going to talk about scatter modes, and I will try and be very brief here.
Hey Wes, I'm actually going to click off. I've got an early morning tomorrow, so
Okay,
I'll catch this on the review, on the rerun.
yes.
Okay.
The YouTube video should be up within a couple of days, and I'll let everybody know as soon as it's up.
Okay, I appreciate it. Thank you.
Okay, see you later, Kim.
Good night.
So the ionosphere, we're talking about the ionosphere acting like a prism and bending radio waves, but also it will scatter radio waves in random directions, although the scatter effects are much weaker than the refraction. So backscatter is reflections. Okay, backscatter is reflections from features on the Earth's surface, but they can also be scattered from within the ionosphere. So you can hear signals too distant to be, you can hear signals in what would normally be the skip zone, because they are too distant for ground wave propagation and too close for skip propagation. And there's a picture coming up on this. Scatter and backscatter help fill the skip zone when signals would otherwise not be heard. Although, again, warning, signals that you hear through scatter mechanisms are going to be weaker than the normal mechanism. And you will often hear distortion, fluttering, wavering signals because the path isn't very constant. Because scattering happens over a wider area of the ionosphere. So this illustrates these. If you look at the transmitting station on the left, you can see that ground wave signals reach out a certain distance, and skywave signals come back to Earth at a much longer distance. But in the near part of the skip zone, near part from the transmitter, sometimes the ionospheric layers will scatter signals strongly enough that they come back down to Earth in the normal skip zone. And sometimes the signals that reach the first hop, reach the ground at the first hop distance, will be reflected, will be scattered backwards and refract through the ionosphere back in the direction that they originally came from. So, in other words, sometimes you'll be able to hear signals in the skip zone due to scattering. And last thing I want to talk about NBIS. It turns out that below the critical frequency, you can send radio waves straight up and they come back to Earth at or near your location. So, excuse me. So below the critical frequency, the ionosphere reflects everything, including signals coming from directly below. So it says here above 5 megahertz and up to 40 meters. But if you have an antenna that radiates primarily upwards due to NBIS propagation, you can get very short distance. You can get very short distance reflection and scattering back to Earth within a couple hundred miles. So the way you do this is to place a horizontally polarized antenna close to the ground, so that its radiation pattern is primarily upwards and not toward the horizon. So this is a picture of how it can go. So if you have NBIS propagation that is reflecting off of the F1 layer, you can see for very high angles, it will come back down relatively near. I mean, here, this is, well, 25 kilometers is about 15 miles. So we're talking out to about 100 miles here on this picture. And it can go up to a couple hundred miles. And if you have a low antenna on 40 or 80 meters, this is generally what's going to happen. You'll hear stations that are close by but not distant, because your antenna will radiate more upward than out toward the horizon, and you'll get NVIS propagation. I want to say also that if you want to work very distant stations, if you want to be a DXer and work 100 countries, the more radiation your antenna puts out at angles of 10 degrees and below, relative to the horizon, the farther your signal will get. So, and in between, for people who can put antennas 30 or 50 feet up on HF, you get results in between, but it's on different bands, it's very common to be able to work all 50 states, and from this part of the US, the northern states, all of Canada from your backyard. Okay, questions, and then we're done. What is a characteristic of HF scatter? A, phone signals have high intelligibility. B, signals have a fluttering sound. C, there are large sudden swings in signal strengths. Or D, scatter propagation occurs only at night. Guesses, anyone?
Yeah, you mentioned fluttering, I think, earlier, so I'm going to go with B.
That's right. It's letter B. It's letter B, fluttering. What makes HF scatter signals often sound distorted? A, the ionosphere region involved is unstable. B, ground waves are absorbing much of the signal. C, the E region is not present. Or D, energy is scattered into the skip zone through several different paths.
Oh,
So
boy.
you showed that diagram with the dotted line. So I would say it's D.
Yeah, see
Skip
how
zone.
easy that is? It's D.
Yeah, I remember that in my mind.
Yeah.
Yeah. Well, so scattering occurs over a wider area of the ionosphere. So there are multiple paths. Why are HF scatter signals in the skip zone usually weak? A, only a small part of the signal energy is scattered into the skip zone. B, signals are scattered from the magnetosphere, which is not a good reflector. C, propagation is via ground waves, which absorb most of the signal energy. Or D, propagation is via ducts in the F region, which absorb most of the energy. This one should be pretty easy too.
It should be, but I'm blanking. Is it A?
Well,
Yes, the answer is A. Only small part of the energy of the signal is scattered. Is scattered by the ionosphere. Most of it is refracted back to Earth through a longer path. What type of propagation allows signals to be heard in the transmitting station's skip zone? A, Faraday rotation. B, scatter. C, chordal hop. Or D, short path.
Scatter, B?
That's right, scatter.
Yeah.
What is near vertical incident skywave or NVIS propagation? A, propagation near the MUF. B, short distance MF or HF propagation using high elevation angles. C, long path HF propagation at sunrise and sunset. Or D, double hop propagation near the LUF.
B.
Speak up.
B? No.
Yes, that's right. It's B, bravo.
Oh, okay.
Using short distance propagation using high elevation angles, and at a low enough frequency that high angle radiation is refracted back to Earth.
Okay.
Okay, so that's it.
Thank you.
Thank you for persisting. Again, I tried to be faster and didn't do a very good job.
No, you did a great job. You did a
No,
great
this
job.
is, yeah, this
A lot
is
of
good.
material. A lot of material.
Yeah, so, excuse me. So now we get 3 questions again. If John's not in town, Marv or I will ask the 3 questions from chapter 4, and then
Okay.
read I guess it's what, chapter 9 is next. We're going to talk
Yeah.
about safety next week.
Yeah.
We're going to talk about the parts of safety we didn't talk about in previous weeks.
I'll be able to get
Well,
that one because
that's kind of fun too.
Yeah.
I'm sorry?
I work with a lot of electricity. I should be able to get that one.
Yeah, some of it. Well, some of it is just common sense. You don't want to put your antenna anywhere near electric
High
power
voltage
lines.
wire. Yeah.
Yeah, some of it is common sense. You want your antennas well anchored and you want towers well guided. And the rest of it, you'll have to read the book.
I know. But there's a lot on grounding straps too.
Yeah.
Yep, yep.
All right.
So
Thank you
thank
very
Thanks,
much.
guys.
Thank you.